This video is all about space trusses. Space trusses are just 3D trusses. So just a reminder, a truss is composed of two force members that are either in tension or compression. The fact that we've moved to 3D hasn't changed that at all. They are connected using smooth joints. In a 2D, we call them pins. In 3D, we'll call them ball joints. The point is the same. They don't provide reaction moments. The third thing that makes a truss is that we only apply loads at the joints. And then lastly, when we're talking about simple trusses, in 2D they were triangles, in space frames or 3D we'll look at tetrahedrons instead. The way that we analyze these is using a process that we've already played with before, where we're going to start by recognizing that we can draw position vectors along each of these members, and then from there turn that position vector into a unit vector. Unit vector multiplied by a magnitude gives us a force vector. Then we can sub all those into equilibrium equations and solve for any unknown forces. The key is that we know in a truss, two force members, tension and compression, the forces act along the members. And so because we know the geometry, we know the direction of the force. The only thing we don't know is the magnitude. And so that lets us write these things in magnitude direction sense form. For example, we could write that the force in member AB is some magnitude FAB times the unit vector that points along AB. In other words, it's going to look like some magnitude multiplied by a unit vector that looks like, say, ABX I hat, ABY J hat, and ABZ K hat. Let's try one out. So, first things first, we're going to do a position vector. Let's say we're looking for the forces in member AE. Well, we start with the position vector by writing the position vector from, say, A to E, which, if we look at this picture, to get from A to E, we're going to make X 2 meters larger, so 2I hat. We're going to make Y 2 meters larger as well, so 2J hat, and we're going to come down by 2 meters in Z, so negative 2K hat, and that's in meters. Next, we will turn that into a unit vector by dividing it by its magnitude, right? UAE is equal to the position vector divided by its magnitude. And so we'll have 2I plus 2J minus 2K divided by square root of 2 squared plus 2 squared plus 2 squared. And both the top and bottom are measured in meters, so they'll cancel. And we're left with 0.577 I hat plus 0.577 J hat minus 0.577 K hat. From there, we'll write this as a force vector. Just to save a little space, I'm just going to do it right here. We can write that take all of the unit vector there and multiply it by the unknown FAE, and that is now the force vector FAE, written like so. Just to clarify here, what we're looking at is an unknown magnitude in that member, but we have a known direction. So that's great because we can break this into components and we can sum forces in each direction. So from here, what we're going to do is break out our trusty equilibrium equations. So if we wanted to, say, look at joint A, we would start with a coordinate system. got Z here, X here, Y there. This is our point A, and looking at the forces here, we have along the y-axis this P force being applied. We have the force in member AB, FAB. We have the force going down to C, so this would be FAC. And we have the force in the member that we're interested in, which kind of comes down diagonally here as FAE. To do our equilibrium equation, we sum the forces in vector form, and we'll still want that to be equal to 0, but now we're just going to write everything in vector form. So we've got P as a vector, plus FAB as a vector, plus FAC as a vector, plus FAE in vector form. Now what we're going to do is just sub all of the definitions of each of these force vectors into our equation. So we can look here and we can see that P moves in the negative y direction, so this will be a minus 4 kilonewtons times J hat. FAB is some unknown, FAB. It moves in the positive y direction, so it gets a J hat. FAC moves in the negative k direction purely, AC, k hat. Now these forces could of course all have components in multiple directions, but this example they don't. And we also have, same line, same equation, FAE. But really what it is we got FAE, the x component, which is 0.577 times I hat plus FAE times 0.577 J hat, and negative in the z direction, minus FAE times 0.577 K hat. And all of that, if this is in equilibrium, has to be equal to a 0. Slide this up. So now what we can do is we can look at this equation and we can solve it as actually 3 equations using each the I, J, and K components because they all have to add to 0. So in the I direction, we simply have FAE times 0.577 I hat. There are no other terms with an I hat on them. This must be equal to 0. That tells us right away FAE is actually equal to 0. There's no force in that member. If we look at the J direction, we have the minus 4 kilonewtons. We have FAB, and we have FAE times 0.577. And that needs to equal 0. Now we got 2 unknowns here, so we can't do much with that yet. Let's go ahead and write out the K equation and see what help we get. Well, we've got minus FAC with a K hat on it. We've got minus FAE with a K hat on it, so 7 gets brought down there, and that's equal to 0. Now we already showed FAE was equal to 0, so this one tells us that FAC must be equal to 0. And if we sub that into our J direction, we can solve and find that FAB is equal to 4 kilonewtons. It comes out positive. We drew it pointing out of the point, so just like other method of joints problems, that means that this is in tension, because we drew our force out and we're doing the sum of forces on the joint. So the trick here, whenever you're dealing with these problems, is to go joint by joint. Sure, you could write out the entire set of forces for this truss, but you'll probably end up spending more time than you needed to. A lot of times you'll discover neat little tricks like this where some of the forces are instantly discovered to be 0, and that makes your life a lot easier. So we've just found the forces in a bunch of these members, and we only had to do it at one point.